We started talking about the zeros of, or the roots of a polynomial. So what we're going to do is we're going to, in our last video, we took the roots and from the roots we found the polynomial. So the roots were given. Now we're going to go the other way. Notice this is called the rational zero test instead of the rational root test, but zeros and roots are the same thing. So what this does is it allows us to find the roots of a polynomial. Now, the rational zero test, what it's doing is it's not finding the roots of the polynomial, it's finding the possible roots of the polynomial. And what that means is that the rest is kind of up to us. Okay, so there's a lot of, the burden is on us to find those roots and what the actual roots are. But what this does is it kind of eliminates a lot of the possibilities. Okay, it narrows it down. So here's what the rational zero test says. The possible zeros. Possible rational roots. So this won't find all of the roots. In other words, it does not tell us if we have irrational roots. It does not tell us if we have imaginary roots. So this is very limited, okay? So the possible rational roots are the factors of the constant divided by the factors of the leading coefficient. Okay, what does this mean, right? I just introduced new terminology that we've never heard before. Okay, so now we have to talk about it. So we have a polynomial. Our polynomial is f of x. Let's go back to way back when we defined polynomial. We had f of x is equal to a sub. Give me a second. I want to make sure that I put it in the same way that I gave it to you, because I can't remember if I put a sub 0 first or a sub 1. So I'm just going to double check. Okay, so we did it as a sub n and then x sub n plus, then we had a sub n minus 1, that was our next coefficient, x to the n minus 1, a sub n minus 2, x to the n minus 2, and then we kept going until we had a sub 1, x to the first, and then plus a sub 0, x to the 0, and remember x to the 0 is 1. So this is really just a sub 0. So what is the constant? The constant is this last term. And what is the leading coefficient? The leading coefficient is the coefficient of the highest power of x. Okay, so we're going to be talking about the leading coefficient a lot when we talk about graphing polynomials. Right now, what the leading coefficient is going to do is it's going to help us find the roots of the polynomial. Okay, so let's just go through a bunch of different polynomials and find all of the different possible rational roots. Okay, so we're not finding the roots, we're just finding the possible roots. Okay, so let's take, for example, so for each of the following polynomials, all we're doing is finding the possible rational roots. And remember, that's the same thing as the possible rational zeros. Okay, this word possible is really important because we're not saying that it's a root. We're saying it's a possible root. Maybe it's a root. And if it doesn't fall within the list that we create, then it's definitely not a root. Okay, so let's start with something relatively simple. Let's start with, so I'm going to number because we're just going to do a bunch of examples. So we're going to start with x to the fourth minus 3x cubed plus 2x squared minus 4x minus 6. Okay, and we're going to find all of the possible rational roots. Now, the fact that this has a degree of 4 is actually irrelevant to us. It could have a degree of 100. A degree of 100 doesn't make this problem any more complicated. Okay, it's really basic. Okay, so what we need is we need to figure out the constant and we need to figure out the leading coefficient. So the constant is this last number here. Okay, the 6 is the constant. That's what we care about. And you don't have to worry about the negative or the positive because that's already going to get taken care of. Okay, so this last number is the constant. And then the leading coefficient is the coefficient in front of the highest power of x. So our highest power of x is x to the fourth. And our leading coefficient is 1. If there is no coefficient, then the coefficient is 1. Because 1 times anything is itself. So what we're doing is we're saying we really don't have to write it. Okay? There's no reason. There's no reason to have extra numbers in there. Same way that for the constant, we really don't have to write x to the 0 because x to the 0 is 1. Okay, so what does this mean? The easiest way to do this is to create a table. Okay, so I'm going to write down here constant is 6. And the leading coefficient, which I'm going to abbreviate as LC. Okay, so LC. I'm going to do that from here on out. So the leading coefficient is LC. Okay, the easiest way to do this is to create a table. You don't have to create a table, but it is the easiest way because it helps you keep track of stuff. Okay, so in your columns, you're going to have the factors of the constant. Factors of the constant go on top. And in your rows, you're going to have the factors of the leading coefficient. Okay, so let's start with the factors of the constant. Well, our constant is 6. So what are the factors? The factors of 6 are 1, 2, 3, and 6. And actually, I'm going to spread this out a little bit more. So I'm just writing the same exact thing. I'm just spreading it out. Okay. And then we have the factors of the leading coefficient. Well, the leading coefficient is 1, and the only factor of the leading coefficient is 1. So now we have our table. So this one is a really easy table because there's only one row to it. Okay, what's going to go inside these boxes? Inside these boxes are going to go the constant over the leading coefficient. Okay, so in each of these, you're going to put the column over the row. Right? It's the factor of the constant over the factor of the leading coefficient. And because everything could be positive or negative, you could have a plus or a minus. For each of these, what we're going to do is we're going to put a plus or a minus in front of it. Okay. So let's do that. So here we have 1 over 1. And simplify it. That's 1. Plus or minus. Here we have 2 over 1. Plus or minus. 3 over 1. Plus or minus. And 6 over 1. Plus or minus. Okay, which means that here are our possible rational roots. You don't have to write this list. I'm doing it so that it's an easy summary. But if you leave it inside the table, that's okay. Just be really careful that you're including these plus or minus. And technically, we would want a plus or minus in front of each of these, right? Okay, so everything has a plus or minus. So this was a nice simple one because their leading coefficient was 1. Let's take another one. Let's say that we had f of x Okay, this is a little slow because a lot is going on. So f of x is equal to, and this time let's make it 4x to the 5th minus x squared plus 12. So now we're going to do the same thing. We're going to identify our constant and we're going to identify our leading coefficient. So our constant is the thing that doesn't have a variable. Our constant is 12. Our leading coefficient, well, our highest power is 5. That's the degree of this polynomial. And the coefficient there is 4. So we're going to create a table. So we're going to have the factors of the constant on top. And we're going to have the factors of the leading coefficient on the side. So let's start with the factors of the constant. So the factors of a constant are factors of 12. So there's 1, 2, 3, 4, 6, and 12. So just be careful that you don't forget, okay? So sometimes it can be helpful to think about it in terms of pairs So we have 1 and 12, 2 and 6, and 3 and 4. Okay, so 1, 2, 3, 4, 6, and 12. That's what goes up on top. Then on the side, we have the factors of the leading coefficient. So now we need the factors of 4. Well, we have 1 and 4, and we have 2 and 2. So we don't need to put the 2 twice. We would just put 1, 2, and 4. And we're just going to create our table. So remember, it's the column over the row. That's important. How can we remember that? Well, alphabetically, column comes before row. I don't know if that's helpful to you, but you kind of just have to remember. Okay, column over row. If you can simplify in your head, that's fine. Okay, I'm not going to simplify until afterwards, so I'm going to write it in unsimplified form. In other words, as the column over the row, and then I'll simplify, just so that you get accustomed to column over row. Okay, so this is plus or minus 1 over 1. That simplifies to plus or minus 1. This is plus or minus 2 over 1. Obviously, if you simplify it in your head, it's going to make this go faster. It's also going to make it look less crowded, okay? Plus or minus 3 over 1, that's plus or minus 3. Plus or minus 4 over 1 is plus or minus 4. Plus or minus 6 over 1 is plus or minus 6. And plus or minus 12 over 1 is plus or minus 12. And actually, I just have to remember that it's column over row. That's not that hard to remember, okay? And the reason why it's not that hard is think back to a quadratic. When you're factoring a quadratic, you're looking for numbers that multiply to the constant. So all of these numbers, all of the factors of the constant should definitely be possible rational zeros, okay? So you know that you're going to have each of the constant factors as a possibility. And we do 1, 2, 3, 4, 6, and 12. If you switched it and you did row over column, that's not going to happen. Okay. Okay, let's keep going. The next one is plus or minus 1/2. That doesn't simplify, so we leave it. Then we have plus or minus 2 over 2. Now this is plus or minus 1. We already have this, so we're going to cross it out. There's no reason to repeat it. Okay, then we have plus or minus 3 over 2. Doesn't simplify. Plus or minus 4 over 2. That's the same thing as plus or minus 2. Okay, we'll cross out afterwards any repeats. Okay, then we have plus or minus 6 over 2. Again, this is repetitive. Plus or minus 3. That's also going to wind up getting crossed out. We have plus or minus 12 over 2, which is plus or minus 6, also repetitive. Then we have plus or minus 1 over 4. Plus or minus 2 over 4. That's the same thing as plus or minus 1/2. So this will also get crossed out. Plus or minus 3 over 4. Plus or minus 4 over 4, which is plus or minus 1, that will get crossed out. Plus or minus 6 over 4, that's the same thing as plus or minus 3 over 2, that will get crossed out. Plus or minus 12 over 4, that's plus or minus 3, also will get crossed out. So we actually have a lot of repeats, okay? So we're going to cross out each of the repeats. Top row is never going to be repetitive. Bottom row, 1/2 we keep, 3/2 we keep. 2 we already saw in the top row, so we're going to cross that out. Plus or minus 3, we already saw that in the top row, we crossed it out. Plus or minus 6, it's in the top row, we crossed it out. 1/4 we don't have yet, we keep it. But plus or minus 1/2 was up here, so we cross it out. 3/4 we keep. Plus or minus 1, that could get crossed out. Okay, we had that already. Plus or minus 3/2, we had that already as well. That was up here. And then plus or minus 3. So this looks like it's a lot of different possibilities, right? It's the number of things in the row. We have the number of rows and columns. So between the number of boxes in this particular one is 18 boxes, okay? But, which means we have double the roots because it's plus or minus for each one. So it looks like we have 36 possible roots, but we don't because we have repeats. So out of those 36, we're actually taking out 16. So we only have 20 possible roots. How do I know we're taking out 16? We crossed out 8 boxes. For each of those 8 boxes, there are 2 possibilities, plus or minus. So that's 16. 36 boxes minus 16. Okay, 36 roots from the 18 boxes minus the 16 gives us 20 possible roots, which is a lot. To try all of those 20 roots, that's a tremendous amount of roots to try, okay? But 20 is a lot better than an infinite number, okay? Let's do another one. Notice I didn't write out the list. It's okay if you don't write out the list. If you leave it like this, I'm okay with that. But you must cross out the repeats, okay? Let's say, for example, that we have 2x to the 5th plus 19x to the 4th plus 68x cubed plus 114x squared plus 90x plus 27. Okay, and remember, the degree is irrelevant, and all of these big numbers in the middle, irrelevant. The only ones that we care about are the constant and the leading coefficient. And what we really care about is how many factors they each have. The less factors that they have, the easier this is going to be. Okay, so here our constant is 27. And our leading coefficient is 2 here. So we're going to do the factors of the constant. So we are just creating our table. Factors of the constant. On top, the factors of the leading coefficient on the side. So 27. Well, 27 has the factors 1 and 27, and 3 and 9, and that's it. And 2 only has 2 factors, 1 and 2. So notice this was not complicated, even though it actually looks a lot more complicated than the second example that we did, but we actually have far less possibilities because here we have 4 columns and 2 rows, which is going to give us 8 boxes. Okay, 4 times 2 is 8. And then since in every box we have a plus or a minus, that's 16 possible roots. And we don't know. It's possible that there are going to be repeats, unlikely in this case, okay, because there are only 2 rows. So let's fill it in. And just to eliminate any sort of extra confusion, let's simplify some of this, okay, just in the first step. So in the first row, we know that we're always dividing by 1. And dividing by 1 doesn't do anything. So in the first row, we just have plus or minus 1, plus or minus 3, plus or minus 9, and plus or minus 27. So instead of writing 27 over 1 is 27, we're just going to write plus or minus 27. Okay? Okay. Then, second row, we have plus or minus 1 over 2, plus or minus 3 over 2, plus or minus 9 over 2, and plus or minus 27 over 2. And none of those can be reduced in any way. So this we actually would have 16 possibilities. Okay, so it's a lot. It's not that this is simple. This tells us one of these is a root, but we don't know which one. Okay, so we would have to try them all, and we'll talk about that in a minute. Let's do one more, and then we'll talk about how to actually find some roots. Okay. So let's say that we have f of x is equal to, let's do 16 x to the 8th plus 48 x to the 4th minus 3 x cubed plus 25 x squared plus 9. Okay. Again, this looks kind of complicated, but don't be fooled, right? It's not the degree, it's not the coefficients, it's only the leading coefficient and the constant that matter. So again, we're going to identify the constant, which is 9. We're going to identify the leading coefficient, which is 16. And then we're going to do exactly what we've been doing. Factors of the constant, factors of the leading coefficient. So here, 9 doesn't have all that many factors. So the factors of 9 are 1, 3, and 9. Then we have the factors of the leading coefficient on this side. So the factors of 16, they're an extra. We have 1, 2, 4, 8, and 16. So there are more possibilities here, right? We have 5 rows and 3 columns, so that gives us 15 boxes, meaning that we have 30 possibilities. But we don't know. It's possible, we don't know, it's possible that there's some repetition. Okay, and if there's repetition, you cross out. If there's no repetition, there's nothing that you can do. There are 30 possibilities. So we're first going to fill these in, and then we'll look for the repetition. And again, I'm not guaranteeing that there is, okay? Typically, in a lot of cases, you have at least some repetition, but it kind of depends on the factors and whether there are any factors that they might have in common. Okay. So we have 1 over 1, which is plus or minus 1. Then we have plus or minus 3, plus or minus 9. Now we have 1 over 2, so plus or minus 1/2. Plus or minus 3/2, plus or minus 9/2. So far, no repetition. Then we have plus or minus 1/4, plus or minus 3/4, plus or minus 9/4. Still no repetition. Plus or minus 1 over 8, plus or minus 3 over 8, plus or minus 9 over 8. Unfortunately, still no repetition. Plus or minus 1 over 16. Plus or minus 3 over 16. Plus or minus 9 over 16. Unfortunately, every one of these is different. There's nothing that we could cross out. So yeah, there are 30 roots here. 30 possible roots. Okay. So let's talk a little bit about what kinds of problems we're going to have when we do this, because to test all of these roots would be crazy, right? And how can we test to see if they're roots? Well, there are a few different ways that we could do it. we can use synthetic division, okay? Where we're saying, okay, well, if these are the factors of the leading coefficient, if we're considering that these are roots, we can use synthetic division where we use this as the polynomial, okay? And we put 1 in that little box. We put -1 in that little box. And we do synthetic division and see if the remainder is 0, okay? That would be one way of doing it. This is a case where the remainder theorem could come in really helpful, because instead of doing synthetic division every time, we could plug in 1, okay? See if you get 0. If you don't, then this is not a root. We could plug in -1. If we don't get 0, this is not a root. And you could do that. Still pretty cumbersome because you have to do it with 30 different numbers. But that's the approach that you would take, okay? Synthetic division, see if you get a remainder of 0 where these numbers go in your box, okay? And f of x is your polynomial. Or the remainder theorem. And the remainder theorem would be you plug these numbers into the polynomial and see if you get 0, okay? It's really kind of like the factor theorem. Remember, factor theorem and remainder theorem are essentially the same. The remainder theorem says when you plug it in, you get the remainder. The factor theorem says, hey, if that remainder is 0, then we know that this is a factor or our number is a root, okay? Okay, we're going to do 2 examples where we actually go through what a problem would look like, okay? So an example of an actual problem that you would get. So we're going to need a little bit of space. So I'm going to turn the page, and we're just going to go through 2 of these, okay? We don't need to go through a lot because we're essentially doing exactly what we did here, okay? So I'm going to write the whole problem down, and then we're going to go through it piece by piece. So example 1, and this kind of puts together everything that we've been talking about in polynomials, most of what we've been talking about, okay? So given is equal to 2x cubed minus 13x squared plus 10x plus 25. We're going to do 4 things, okay? The first thing, we're going to find all possible rational roots. So we'll practice that again. Then we're going to help you out. We're going to say, use synthetic division or the remainder theorem, and we'll probably do both just so that you see how you would use both, okay? To show 5/2 is a root of f of x. So that's going to be the second thing. Then we're going to find the remaining roots. And finally, we're going to write the complete linear factorization. So you obviously don't have to multiply because we already know what the polynomial is. Okay, so 4 things that we're going to do. So let's do it one piece at a time, okay? And none of these are that complicated. This is a very long problem, no doubt. We're being asked to do 4 different things. We're being asked to find all the roots. We are given one of the roots to help us along, okay? But none of these individual steps is particularly difficult. So take it one step at a time, okay? So part A, we want to find all possible rational roots. So we've been doing this. We need to identify the constant. And by the way, you should try and do this on your own. You are capable of doing this on your own at this point. You know how to do everything. But if you want to sort of sit and watch this one and do the next one on your own, that's okay. So let's say that we have a constant. Our constant is 25. And our leading coefficient here is 2. Okay. So we're going to create our table. Factors of the constant. Which fortunately here there aren't that many. It's just 1, 5, and 25. And then we're going to have the factors of the leading coefficient. Again, fortunately there are not that many. It's just 1 and 2. So this means that there are only 12 possible roots. Okay. So let's find them. So we're just creating our table here. So 1 over 1 is 1, so this is plus or minus 1. This is plus or minus 5 over 1, which is just 5. And plus or minus 25 over 1, which is just 25. Plus or minus 5 over 2, and plus or minus 25 over 2. Okay, and there is no repetition here, right? We don't see any repetitive values in this table. What we do see is part B, right? It says show that 5 over 2 is a root of f of x. Well, we already know that 5 over 2 is a possible root. So what we're asking for is show that it's an actual root. Okay, so you do not have to do this in both ways. You only have to do it in one way. But I'm going to do it in both just so that you see how it works. So notice it says or the remainder theorem. Okay, so let's do this. Okay, so let's use the remainder theorem first. So the remainder theorem says if we plug in 5 over 2, and we get 0, then 0 is the remainder, okay? Factor theorem says 5 over 2, that 5 over 2 is actually a root, meaning x minus 5 over 2 is a factor, okay? So we're going to do f of 5 over 2. And we're going to plug it in. 2 times 5 over 2 cubed minus 13 times 5 over 2 squared plus 10 times 5 over 2 plus 25. And don't be afraid to use your calculator. That's okay. You don't have to do all of your fractions, okay? Essentially what you can do is you could plug in 2.5 because 5 over 2 is 2.5. It's an exact decimal, so you could plug it in as 2.5 and not run into trouble. And if we plug this in, we do in fact get 0. And this is where the remainder theorem can be really helpful because this was a relatively short process and now we know 5 over 2 is a root. If we plugged in negative 5 over 2, what you're going to find is that you won't get 0, okay? You won't get 0, which means that negative 5 over 2 would not be a root, okay? That's using the remainder theorem. Let's do synthetic division. And actually, the advantage of doing synthetic division is that you're going to have to do it anyway to find the remaining roots, okay? And there are multiple ways that we could find the remaining roots, but the most efficient way is to use the synthetic division. And this is why, even though everything can be done using long division, and you can do it using long division too, by the way, synthetic division is much faster, okay? So in our box, we have the 5 over 2, and then we have the coefficients of the polynomial. Check that it's in standard form, and it is. We see 3, 2, 1, and 0 as our exponents, so it's in standard form. So in our top row, we have 2, negative 13, 10, and 25. Okay, and our goal is not to make this hard on you. So in these problems, the synthetic division is not going to be difficult, so don't panic, okay? So we carry down the 2, and 2 times 5 over 2, the 2's cancel, so we get 5. We add negative 13 and 5 is negative 8. And again, negative 8 times 5 over 2, well, that's going to give us negative 4 over 2, or negative 20. So you're getting integers. I'm not going to make you add fractions, okay? 10 and negative 20 gives you negative 10. Notice all of these are even numbers, so they're all divisible by 2, making your life easy. And that's going to give you negative 25. And 25 and negative 25 is 0. So yes, you get a remainder of 0. This is a root, okay? So the only thing that you want to do is you just want to be really clear about why it's a root, okay? So you could put a check mark next to it, but just say remainder equals 0. Okay, and that's just going to make things easier in terms of making it really clear what you're doing, okay? Because otherwise, synthetic division, it's not really clear. The remainder theorem, putting the check that it's equal to 0, is saying, okay, we want it equal to 0. Putting the check here, you just want to make it clear that it's this last number that you're looking at, okay? And then here's why the synthetic division is useful. Because in order to find the remaining zeros, now we have a smaller polynomial. Because if it's a factor of this polynomial, then it's also going to be a factor of this one. Think about it this way. If we said that something is a factor of 8, then it's also a factor of 16. So we're saying if it's a factor of the smaller polynomial, which is a factor, then it's a factor of the bigger polynomial, okay? So if we have something that's a factor of 8, that's going to be a factor of any multiple of 8. And 2x cubed minus 13x squared plus 10x plus 25 is a multiple of this polynomial down here, which, if we put in our x values, negative 10x to the 0, negative 8x to the first, and 2x squared. So this gives us a smaller polynomial that we can work with. And that's important because now we have to find the remaining roots. Okay? So this brings us to part C. The disadvantage of using the remainder theorem is that then your only other option, if you don't do division afterwards to get a smaller polynomial, is to try each of these others. And unless you're lucky, it may not work. And what if all of the roots aren't rational, right? We can have imaginary roots. So there's a disadvantage to using the remainder theorem over synthetic division. Both accomplish the same thing, but synthetic division moves you a step further when you have to find the other roots. Okay, let's do part C. So part C asks you to find the remaining roots. So what we're doing is we're finding the remaining roots of 2x squared minus 8x minus 10. And one thing that we can do here to make our lives easier, we know how to factor, okay, quadratics, we know how to do that. But one thing which can make our lives easier is we can actually factor out a 2, okay? Don't ignore it, just factor it out. Okay, which means that this is going to make it easier to factor because we don't have to worry about an a greater than 1. So we're looking for two numbers that add to our b and multiply to our c. So our b is -4. So we're looking for two numbers that add to -4 and multiply to our constant, right? And those two numbers are going to be -5 and +1. So if we put this in, we have 2 times x minus 5 times x plus 1. So one root was 5/2. Our other roots we can find by setting this equal to 0. Now 2 is not 0, but that doesn't matter, because if x minus 5 is 0, then the whole thing is 0. If x plus 1 is 0, the whole thing is 0, so it doesn't matter. So we're saying x minus 5 equals 0, or x equals -1. X plus 1 is equal to 0. I got ahead of myself a little bit. Okay, and then our roots are x equals 5 and x equals -1. Okay, so that gave us our remaining roots, but now we need the complete linear factorization. So that's really straightforward here. All that's doing is asking us to write all of our roots, and we already have. It's asking us to write all of our facts, and we already have factors. So we know that we're going to have a 2, x minus 5, x plus 1, that was already there. And then x equals 5/2 is a root. So let's set this equal to 0. Now some of you are setting it equal to 0, and the way that you're doing it is you're just subtracting 5/2. You can do that, but typically our polynomials, we don't want fractions. So what you want to do is you want to multiply by 2 first. Okay, this gives us 2x is equal to 5. And then we can subtract 5 from both sides. Giving us 2x minus 5. This is the neater way of doing it because our polynomials should not have fractions. So this is our third one, 2x minus 5. And we're done. This is our complete linear factorization. Okay, I'm going to box it so that you know. Okay, example 2. So same exact thing. Given f of x is equal to 5x cubed minus 16x squared plus 13x minus 2. Okay, we're going to do all of the same things. So we're going to find all possible rational roots. Okay. We're going to use either or, so you don't have to do both. Synthetic division or the remainder theorem. to show this time that 1 is a root of f of x. Then we're going to find the remaining roots. And again, there are two ways to do this, so we'll talk about both ways when we get there. And finally, and this is the shortest part, once we have the roots, then it's really simple. We're just going to write the complete linear factorization. So we've done all of these, and as I go through, I'll tell you which videos to listen to if you're struggling, so that you remember where to go. So part A is what we've been doing in this video, okay? We're going to find all possible rational roots. So if you remember, the only things that we need to identify are the constant, which is 2, and the leading coefficient, which is 5. And this is actually really nice for us because they're both prime numbers, which means that both of them only have 2 factors. So we're going to put in the factors of the constant. Factors of the constant are just 1 and 2. And then off on the side, we're going to put the factors of the leading coefficient. And that's just 1 and 5. So also prime, so really nice that it's very small amount here. Okay, and that 2 did not come out. Okay. So we're just going to fill in our boxes. And what's nice is this means that there are only 8 possible roots, all 8 possible rational roots, okay? So 1 over 1 is 1, so our first one is plus or minus 1. Then we have plus or minus 2 over 1, or plus or minus 2. Plus or minus 1 over 5, that cannot be simplified, so we just leave it. Plus or minus 2 over 5, also can't be simplified. So there are only 8 possibilities here, okay? And this is a plus or minus. Okay, that's it here. There's no repetition, you wouldn't cross out. We're done with part A. Part B. So we're going to do this both ways. Okay, we're going to use the remainder theorem, and we're also going to use synthetic division to do this. So the remainder theorem says, okay, well, if we plug in the root and we get 0, then the remainder is 0, and factor theorem says, okay, that means that x minus 1 is a factor. Okay, because we're talking about factors versus roots. So we could just plug in f of 1, and our goal is get 0. If you get 0, it's a root. If you don't get 0, it's not. So 5 times 1 cubed minus 16 times 1 squared plus 13 times 1 minus 2. And this, it's 1, so it makes it easy. 5 times 1 cubed is 5. Negative 16 times 1 squared just leaves us with negative 16 because the 1 doesn't change anything. Then we have plus 13 minus 2. And 5 minus 16 is negative 11. Plus 13 is positive 2. Subtract 2 from that, and you get 0. So yes, this is a root. So yeah, we did what we needed to do. Okay, let's do this using synthetic division too. So the advantage of synthetic division is to help us with part C. But you don't have to do it, okay? And you can do one or the other. So let's do the synthetic division. What the synthetic division is doing is it's actually dividing to get a quotient, so a polynomial that theoretically could be a factor of our bigger polynomial, of our f of x. So inside our box goes our root. And then we go up here and we double check and we make sure that this is in standard form. So we look at the exponents. 3, 2, 1, 0. The exponents go down by 1 and they end at 0. This is in standard form. So now we can just write our coefficients. 5, negative 16, 13, and negative 2. Okay. Remainder theorem is in the last video on synthetic division. So these two things are both in the same video from previous week. The 5 we carry down. Then what we're going to do is we're going to take that we're going to take the 5 and we're going to multiply it by the divisor. So 5 times 1 gives us 5. And then we just add. So negative 16 and 5 is negative 11. Negative 11 times 1 is negative 11. 13 plus negative 11 is 2. 2 times 1 is 2. And negative 2 plus 2 is 0. So yes, this does work. The remainder is equal to 0. So remember, you want to write this so that it's clear what you're looking for in the synthetic division. Okay? And then we're going to actually write our quotient because that's going to help us with part C. So we could put in this next to the 2 is an x to the 0, so we don't have to put anything. Then we have x to the first, and then we have x squared. And there's no operation between here, so we put a plus sign. Okay, so now we're done with part B. We showed that 1 is actually a root. So now we're doing part C. So part C, there are two different ways to do it, if you remember from the last time. One way is going to be more efficient and less risky than the other. So we could use the remainder theorem and test all 7 of these other roots. Now, it's a polynomial of degree 3. So if you remember, that means that there are 3 roots. We already found one of them. So we could try the other 7 possibilities using the remainder theorem. Plug in negative 1, plug in 2, negative 2, 1/5, negative 1/5, 2/5, negative 2/5. You hopefully will get 2 more that give you a 0, and those would be your 2 remaining roots. The disadvantage of this is, one, it's a lot of work. You're plugging in a total of 8 numbers, okay? And if there were 16 possibilities, you're plugging in even more. So that's the first disadvantage. The second disadvantage is you're assuming that the rest of your roots are rational. And remember, we said you can have roots that are imaginary. You can have roots that are irrational. So what you're doing is you're taking that risk. Okay. The safer bet is using synthetic division, which is what we're going to do because it's shorter and it is the safer method. So remember that if it's a factor, if you get a factor of 5x squared minus 11x plus 2, that's also a factor of the bigger polynomial. Okay, we said a factor of 8 is also a factor of 16 because 16 is a multiple of 8. If you have a factor of 9, that will also be a factor of 27. A factor of 10 will also be a factor of 100 because these numbers are multiples of the smaller numbers. So a factor of the smaller number is also going to be a factor of the bigger number. So if we could find the roots of this 5x squared minus 11x plus 2, those are also roots of this 5x cubed minus 16x squared plus 13x minus 2. Okay, so let's do that. So we already know how to do this. We're just going to, in order to find the roots, we can complete the square if we want. That's kind of annoying in this particular case because we have 5 and -11. They're not divisible by each other. We're going to wind up with a lot of fractions. We can use the quadratic formula. That's fine. It's more work. In this case, factoring is going to be easier, but again, we know the quadratic formula works. We're going to factor. Okay. So we have 5x squared minus 11x plus 2. Okay. Whoops. Sorry. This, I forgot to... I paused the tape and then I forgot to restart it. So I did this video and now that's the second time that I'm doing this part of the video. So I'm going to take away all of the stuff that I wrote so that you're not seeing it beforehand. I think it's easier if you're watching it as I go. So you had all of your answers there, but now I'm taking them away. We're going to rewrite exactly the same thing. So just ignore what you saw. Pretend it didn't exist. Okay. So we want to factor this. What are we going to do? We're going to start by multiplying a times c. So this is from, go back to factoring quadratics if you're having trouble with this. So our a is 5, our c is 2. So when we multiply, we get 10. And then what that means we're looking for is two numbers that multiply to 10, but add to -11. Okay, so what are those two numbers? We do have two numbers, so this is factorable. Okay, 10 and 1 are factors, and they will add up to -11 as long as they are both negative, and that's okay. -10 times -1 gives us a positive 10. Okay, so what do we do from there? We replaced the b term with this -10x plus -x, right? So we're going to rewrite this, but instead of -11x, we're going to use the -10x minus x. So it looks like this: 5x squared minus 10x minus x plus 2. Now it's a factor by grouping. So we group the first two terms and the last two terms. So out of the 5x squared minus 10x, we can take out a 5x. 5x goes into both of those, which is going to leave us with an x minus 2. From the second group, we can take out a -1. So remember what we said. We said if it starts with a negative, pull out the negative. So since there's nothing else in common, we just pull out a -1. We're left with x minus 2, leaving us with x minus 2. And then from the first group, we get a 5x. And from the second group, we get the -1. Now, all this does for us is find the factors, but remember, our goal in part C is to find the roots. So we have to set this equal to 0. And then each of our factors has to be set equal to 0. And then we just solve. So in the first one, we're adding 2 to both sides. That gives us an x equals 2. In the second one, we're adding 1 to both sides. Leaving us with 5x equals 1. And then we just have to divide both sides by 5. So our root is x equals 1 over 5. And again, in the interest of clarity, something that you're going to want to do is just say, okay, now I know what the roots are. just what you're doing is you're saying, I'm done here. Here's the final answer. So that nobody is going searching for your answer. Our roots are x equals 2, x equals 1 over 5, and x equals 1. And this is part C. So we found the remaining roots. So the last part is the linear factorization. Okay. And again, this is something that we did. We did it in the video on finding the polynomial from the roots. And I'll do this quickly on the side. You kind of already have it because you have the factors over here, but we'll just write it out again. If you remember, we write out each of the roots. So we have x equals 2, x equals 1, and then we have x equals 1 over 5. For x equals 2, we subtract 2 from both sides. That gives us the x minus 2 is equal to 0, which we already know from up here, right? We already have that x minus 2 equals 0. So we're just repeating work, so you don't have to do this. We subtract 1 from both sides. We get the x minus 1. This is the only one that you might want to do since you weren't given the root. Since you weren't given the factor, you were just given the root, but that's how we get it. And then this one we already have from above, but we multiply both sides by 5. Remember, you don't want a fraction, so you want to get rid of the fraction. Okay, that gives us 5x equals 1. Subtract 1 from both sides, and you get 5x minus 1 is equal to 0. So now you have your 3 factors. So our complete linear factorization, so our final step is just to write all 3 of these out. You have x minus 2 as your first factor, 5x minus 1 as your second factor, and then x minus 1 as your last factor. And of course, you can always check it by going and multiplying these out and making sure that you get f of x. I also want you to notice that we said that your other 2 roots are 1/5 and 2. So if you had used the remainder theorem and plugged in the other 7, 2 of them would have worked, the 1/5 and the 2. Nothing else would have worked, okay? You're not going to get more than 3 that work in here because it's a polynomial of degree 3. You will only have 3 roots. Only 3 will work, okay? And that's it.